start with the forecasting and cross-validation. So in this chapter, so again, you guys open a new tab and get the our markdown code as well. I'm not going to be running it during these demos now, but we can run it later during the practice. So roughly speaking, we're going to talk about cross-validation, and then we're going to do a couple of case studies. But the most important part of this specific chapter is to show you 8 alternative strategies for clustering and then comparing them all with one data set. It doesn't mean that that's how they rank. It simply means that on this data set, that's what we get. So I wanted to show the consistency of the protocol no matter which classification or clustering method you use. So, all right, there's a little bit you may want to look back as how to assess in chapter 13. We should all be familiar with the simple metrics for accuracy: false positive, false negative, positive predictive value, negative predictive value, log odds ratio, and other metrics for quantifying you know, multinomial or polytomous outcomes, as well as for continuous features. If you're predicting a feature that's continuous, you got to use slightly different metrics: R-square, correlation, mean square error, etc. So overfitting simply refers to the process of your model or your strategy fitting so well to the data that it actually describes not only the biological or the physical phenomenon, but it describes the noise that is native into the system. So, you know, there is a few examples. Let's not worry too much about some of these details. Look at them if you want to read through a little bit about it if you're interested in overfitting. So, we already actually looked at several examples of cross-validation. Again, the basic 4 steps are as indicated here: partition the data, perform the analysis, validate, and repeat. That's what it is. Here's the example with the linear regression, and again, this is a slightly different point of view. The outcomes, constants, design matrix, effect sizes. You're of course interested in the effect sizes. The root mean square is, as it suggests, square root of the mean deviation of the predicted versus the response. Oh, one important thing here is that when you estimate the root mean square on the training data itself, this error rate of misclassifying or incorrectly modeling on the same data that you trained on does not imply that the same rate of failure is going to carry on to a new prospective data. Okay? So typically, as one can expect, on new future data, the error rate is expected to be higher. That's natural to expect, okay? So if you let your E represent the expected error on the testing or validation data set, so this is the real error rate on the prospective data, then the training data error rate in the linear model case has a closed form analytical expression. People have worked that really beautifully for ordinary least squares estimates. The error rate, as you can imagine, see this coefficient, you guys, in front of the error is less than 1. Okay? So which means that the training error is going to be lower than the testing error, and it's exactly known by how much. So in other words, if all you care about is linear models, you don't have to validate on testing data. You don't, because it's known exactly what the error rate is going to be by computing the root mean square on the training data. Is everybody here with me? However, this is not the case in general. For regularized regression, for model-free techniques, there is no such a simple linear relation to tell you how much the error is going to increase or decrease. So that's exactly why cross-validation is necessary. Okay? And there is two types, exhaustive and non-exhaustive. Exhaustive are these ones that literally do the searches in all possible arrangements between how to split the data into testing and training. And non-exhaustive are more structured things that are more computationally efficient. So here's a Parkinson's disease study using adaptive boosting, another method for prediction and classification. I'll skip over it here just to get to sleep data. Let's not worry about it. That's a very well studied data set. Attitude test, let's skip that. The Parkinson's disease data that we've looked at before is interrogated again here. The important thing is that the summary, the cross-validation output that you get at the end has three components. The first one is the stat.cv that includes a vector of statistics returned by the predict function for each cross-validation run. The stat is the mean statistic, and the SE is the variability of the corresponding statistic. So here is where I want to now go ahead and compare 8 different strategies for prediction. The first one, logistic. So this is also the Parkinson's disease data. So logistic regression is the first one. This is a standard, you know, we read the data in, we define the output as being the diagnostic class as a factor variable, and then we're going to remove that diagnostic label and all the other irrelevant features from the design matrix, which we call the input. And then we go ahead and fit in the simple ordinary least squares logistic model to this data. And this is a very important operator here, confusion matrix. The confusion matrix tells you for polytomos, for multinomial outcomes, how well did the algorithm do to predict each of the levels or the categories of the outcome. So I'll show you, we will see many examples of confusion matrices, but basically they take two vectors. One is of the test Y, the test outcomes, and then the predicted Y outcomes. And in this case, because I have a binary classification into patients and controls, you need to specify which one is the negative case. And then, okay, so here is for each iteration of the cross-validation, it reports, okay, so this is fold 1, iteration 1, false positive rate 1, true positive rate 50, 31, true negative, and false negative 2. In other words, the error rate, you guys, is these 2 false negatives and this 1 false positive. And you see these 4 statistics change between different iterations and different folds. I've simply reported here 5 folds and 2 iterations each because that's what I specified in the code to the cross-validation, right? Typically you'd have k equals to at least 5, sometimes 10, and the iterations could be 5, 10, more. And then diagnostic plots, I oftentimes use in my papers diagnostic error plots because it reports the accuracy of the algorithm, the sensitivity and specificity, positive and negative predictive power, and log odds ratio. So you see, in this specific case, the logistic classifier did pretty good, you know. Both sensitivity and specificity exceeding 93%, that's pretty nice. The second one is quadratic discriminant analysis.
Question.
Yeah.
What if classes are unbalanced?
Right. Well, okay, so unbalanced. Two important things to watch there. Unbalanced and small sample sizes, it's a problem. Unbalanced and large sample sizes is not a problem as long as the probabilities of these imbalanced classes are not very close to zero. In other words, you don't have a class that is only observed 0.5% of the time or something like that. It's difficult exactly to give you a rule of thumb, but remember what I said earlier when I mentioned that rebalancing using the synthetic minority oversampling is necessary when you go into the single numbers. This class is only observed 3 or 4 times. It's too rare to really form a scientific inference. But in general, that's not the case. Even if the probability of something is, let's say, 1%, if you have 1 million records, it's perfectly okay. The model is going to work. That's not a problem that they're so imbalanced in their likelihoods. But if the data size is small, then these may not be very stable estimates.
So basically, practically, one of the approach can be to generate more synthetic data, rebalance the classes, then do the further classification.
In the case, right, in the case when your total sample size is relatively small, you may have to do some of that. But it's tricky, right? A lot of people don't like to do that simply because you're synthetically generating data that does not deviate substantially from your small number of observations of the minority class. And that's a problem because you're repeating, effectively what you're doing is you're repeating the very, very narrow strata that you have observed. You repeat it multiple times, so you're very, when you expand it, you're still within the same scope. You don't expand the scope, so it's tricky, you know. I mean, you have to be careful.
So is there some other way how we can do it?
Well, the right way to do it is to just increase the sample size, but it's expensive, it's time consuming. Oftentimes the physicians, they don't have, you know, right now we're looking at ALS, amyotrophic lateral sclerosis. The physician says, I've got 120 subjects in my database. And I'm like, well, with 120 subjects and the amount of variability you see in ALS, you're not going to be able to pull much. And he goes, well, I see 1 or 2 patients a week. And, you know, it's one of those things, it's very difficult. So if that's not possible, then, you know, you may look for, you know, harmonizing and aggregating data that other people have collected. But you got to increase the sample size one way or another.
So what if, like, if we cannot, if it is a constraint that we cannot increase the sample size or somehow, like, the costs, right? So one of the machine learning ways, according to, like, you can think of it, can we increase the number of weights for the, minority classes in the neural networks or some class track?
You can, but what I'm saying is that when you do that, the synthetic data you generate.
No, I'm not generating any synthetic data. That's one of the approach. Another approach can be, we can increase the weights of the, like during learning process of the minority classes.
Read the weights?
Increase the weights.
Oh, increase the weights. Oh, okay. That is a good point, and I'll tell you, you can do that, certainly. I don't know how well it's going to work because it translates exactly as replicating the cases multiple times. That's what it does, increasing their weight. So I'm not sure if you're going to gain what you're going after, because it's not introducing additional stochasticity into the problem. That's what it is. You stay within the same span of what you started with. And that's the crux of the problem. So I don't know, yeah.
Is there any relation between synthesizing the data and the number of features? If the number of features is extremely high, more than 10,000, will it affect if we try to balance and synthesize?
Yes, so there are some relations. I don't know of any specific expression or formula that says a function of the number of features f is going to tell you how many subjects you need or something like that. But there's definitely relations, right? So the more features you have and the fewer the cases you have, the bigger the problem, without any doubt. But where exactly you can say I'm okay, well, you know, I guess the only thing you can say is that I don't know. I don't really know. But I typically, I would be worried if I have one of these one of the clinical types, phenotypes. If I have less than a dozen subjects, I'll be worried a little bit about that. If I have thousands of features, I need to be concerned of collinearity and whatnot. So linear models, dimensionality reduction methods, all these are out. They don't apply when you have even over 100. You know, when you get into the hundreds and thousands of features, all the classical methods, they don't apply. You need to use one of the machine learning methods. So, you know, it needs to be, you need to pedal gently and always run multiple methods and see how consistent or inconsistent they are. If you run these 8 methods and you get totally different results, that's a clue that something is not quite right with your data.
If we have somewhere around 500 subjects and fMRI is there, and we have some features of around 1,000 or 10,000, then is it okay to go for it, or should
that will be okay, except that you should remember, so to get that many fMRI features, you must have done voxel-based analysis or something. So a couple of issues with fMRI and voxel-based analysis, right? The first thing is that things that are nearby are highly correlated, so you get all kinds of effects of, you know, inter-voxel relations and whatnot, number one. And number two, these metrics, I personally prefer to do these things on a region-based analysis. So what I tend to do is I'll parcellate the anatomy, and then over each region, I'll compute some fMRI statistics. Think about the mean, I don't know, some ARIMA model coefficients. You pull some fMRI statistics, it doesn't matter what they are. But you're typically talking about dozens or hundreds of regions. Double, triple that with the statistics, you're still talking less than 1,000 features. Whereas if you go into voxels, an fMRI volume can easily have, you know, 10,000 voxels.
But if we even go for ROI, say it is 116 ROI, so 116 into 116, if we are seeing the correlation, it will be more than, the upper triangle will be more than 6,617 or more than that. So that's again a huge number of features.
And that's okay. Most of these techniques, including the ones that I'm showing you, can deal with the case where K is bigger than N. That's perfectly fine. But it always helps to embed you guys the neuroscience into the statistics. Because the statistics by itself, these methods are not developed to work on these things. They're developed to work on any data. So when you blend the human and the machine intelligence, typically you can get better. So how to reduce the number of thousands of fMRI biomarkers needs to be done cleverly with some clinical or neuroscientific feed into it.
Is there any specific criteria of choosing the dimensionality reduction technique like DCA or elimination like RFE or, you know?
Not really, not really. I have a chapter here that talks about variable selection. You would typically try a couple and see how they work. They're all different, right? I mean, you know, the classical way of doing it is, you know, some kind of a forward or backward selection. You know, nowadays people are doing the regularized for model-based selection. I mean, but again, it's always better to try to embed some of the neuroscience into it. So we have a situation, we call it phenome-wide association studies, PHEWAS, where we literally have tens of thousands of structural and functional derived imaging biomarkers, and our number of cases are hundreds, between 500 and 1,500 subjects. And we have tens of thousands, sometimes 80,000 biomarkers, believe it or not. It's crazy. And it's always difficult. It's always difficult. Sometimes we just completely unbiasedly put it through this, and it generates the top 100. We look at these things, we say yes, no, yes, no. We run it another time. We run it through different algorithms and see what tends to appear more often. Because every time you do statistics of, well, first of all, imaging is very noisy, okay, without any doubt. When you do statistics on that, that becomes even noisier. So there is a lot of variability embedded in these things, and never mind all the correlations and associations between these tens of thousands of imaging-derived biomarkers. So this is and this is exactly why a lot of studies cannot be quite reproduced using someone else's data and someone else's protocols, even if they argue that they use the same techniques. They use different, if not different software, different protocols, different workflows, different parameters, you know. So there is some variation, and you know, science is validation based, right? The fact that somebody cannot reproduce the results doesn't mean your results are wrong. It simply means that we need to come to some kind of a consensus, you know, as to what works and what doesn't. So it's experimental, in a way.
Regarding the neural network, I tried using few algorithms like NLP, CNN, and RNN. The major problem I'm facing, I cannot get the hidden layer, which features are selected so to report which could be the important features. So in such case,
why do you need the hidden layers? You typically never care about the hidden layers.
But then, see, if I want to know which part of the which ROI is getting selected every time, then this will be...
Right. Okay. So now that's an interesting question. The question is, if you use machine learning methods, they act as black boxes. You don't know exactly. It's not like a linear model. Here is the coefficient. I can interpret it. All the effect sizes, there are statistical tests, significant, not significant. I can compute the variances. You know, you completely understood. Okay. Now on the flip side, in the machine learning world, there's no coefficients. You know, the system learns what it learns. You just ask in the human brain, why do we all think differently? Why are some left-handers, why are some are right-handers? Well, there is nobody has come up with human cognition model that works across people, right? So it's one of those things where it's very dynamic and very environmentally impacted. That is, learning impacted. What did the algorithm learn on? So in machine learning, you never ask that question. It's a question that it doesn't make sense in machine learning method. What are the weights? You can extract them actually. You can. But I don't see the point of looking at these weights because they are associated, but they're not descriptive enough by themselves to help you with the interpretation of the results, if you know what I mean. The power of the machine learning says that this, whatever it does, however the magic happens, it can predict, and it has certain rate of accuracy. That's all. And, you know, obviously it may be learning, we all learn irrelevant things, right? I mean, think about how much you've gone through your learning process, some of which, you know, I've had subjects that I took, you know, in college, 20 years absolutely no relevance, and all of a sudden somebody talks about group theory and my ears kind of go, oh, group theory, you know, what are the groups, you know, what are the operations, you know, some of these really cool things that you do in abstract algebra in college that, you know, don't come up, but at some point some cool things happen. So the breadth of the exposure is very important, and that's what these things do effectively. They don't have, that's what they call non-model based techniques, because you don't have a model and you don't have coefficients that you estimate, you simply predict. So
I have a small doubt before.
Yeah.
So I have a general doubt. So what if you have a classifier which has a 0 training error and the classification accuracy is about 90% for each fold? So can we still say that the model is not overfitted and it's still performing well?
Well, okay, so, well, that needs to be experimentally done, right? So, 2 ways to do that. The first one is to repeat the model multiple times and simply look at the evolution, the iterative evolution of the training error. Typically what happens is you go, you know, it kind of goes like this, the training error gets reduced, and at some point overfitting starts, you know, or something like this, and you got to find that optimal value where you got to stop the training process.
For each fold you are telling me to look at it? For each fold? For each iteration?
Right.
So what if we don't get any error for each iteration?
Well, no, you always have error. Unless your data is, let me see. No, you, 0 error, you mean 0 or close to 0? Close to 0, yes. 0, you can never get 0 unless the data is synthetically generated and can be perfectly described. I'm not sure if you can get 0 error.
I'm talking about the case when we have 100% training accuracy and the testing accuracy is above 90% for each fold.
Right. Okay. So
we can still say it's a good classifier, it's not overfitted?
Well, for the overfitting, you have to have well, I mean, it may be overfitting a little bit, but if your testing error is 90%, I would be hard pressed to believe that there is overfitting. I mean, the decision needs to be made on the prospective validation data, and if it's 90%, that's pretty good. I don't think there will be overfitting. There is no evidence unless that error goes down somehow, which is oftentimes the case. Okay, you train on something, you apply it, and then all of a sudden your training error from 90% drop down to 50 or 60% on the testing. That's a very common situation. That is an indicator of something happening, and you got to be concerned of this. But you know.
Do you have an example of 3-class classification?
Yes, we do. I don't know if it's in this section. The Parkinson's disease, where we had the SWEDs, the PDs, and the controls, is a 3-classifier example. The reason why most of the time I dichotomize them is that you can, the confusion matrix is very crystal clear, misclassified, properly classified, done. You know, but I have several examples. In fact, I have examples with 10 classes or so, where you can kind of look at the confusion matrix again. But and remember the one we did with the OCR that had the A's through Z's. So, okay. So just to press on any other comments here. So I want to show you a few. So the logistic was the first model. Now I'm going to do quadratic discriminant analysis. QDA is part of the mass package. All right. So in all of these situations, let me step back here for a second. In all of these situations, you fit the model. Let's remember the protocol. Train the model, test the model, report the results. That's going to be the 3 steps that we always go through. There will be slight variation, you see. The training is always the same, except that you call a different method. Okay. The prediction may vary a little bit, and we already saw some of these. Compute, for example, was used earlier instead of predict. And the confusion matrix doesn't have to be confusion matrix, could be something else, but these are the 3 steps, right? So back here to quadratic discriminant analysis, QDA, learn the model on the training data, use the model to predict on the testing data, extract the new labels for the predicted models, and then report the confusion matrix comparing testing the true labels with the predicted labels. And then here is where you're going to use this predict function QDA in a cross validation, 20 iterations, 5 folds. Oh, by the way, here I left this error message on purpose. That's an interesting thing. You will get many, and somebody reminded me here earlier, in R you're going to frequently get errors, things don't work. Google search the error, Google search the topic, you'll find the solutions. 100,000 developers out there, okay? There's a lot of knowledge base that's available for you. All the answers are out there. Finding them, I agree. You might have to read a few links to find what you're looking for. I left this specific message here because for the QDA, which is a model-based quadratic model prediction, you have to have independence of the prediction features, you guys. If they're collinear, you've got a problem, and that's the problem that the QDA is reporting here. It basically says rank deficiency in group 1. Rank deficiency simply means some of the matrices are lower ranked than they need to be. The inversion of the matrices or the matrix multiplications cannot be computed, and the reason for this most of the time is that you've got these collinear features. Now, if I remove some of these collinear features, the QDA is happily going to cruise along. Now, the first method, the logistic, didn't care about it, although it also requires independence of the predictors, but I kind of scrapped that, you know, I ignored it. So I'm vaguely violating the assumptions of the model, but so what? Accuracy 92% or something, I'm happy, you know, you move forward. QDA, not so much. So after I remove some of these collinear features, QDA is happy and reports the results. Now here you increase the accuracy, sensitivity. Oh, the specificity dropped a little bit, which is a bit of a concern, but overall log odds ratio still 5 point something, not too bad. Oh, I beg your pardon. Let me see which one is which. The logit is the second report, and it did have slightly higher log odds ratio. So QDA, maybe because we dropped some of the features, you know, it's not clear. But again, overall, not too bad. Here's a little bit if you want to know about QDA and LDA, linear discriminant analysis. Some of the math. We are also going to feed in LDA from the same mass package to the very same data, precisely the same thing, replacing the L by Q, replacing the Q by L, computing the corresponding matrix. Let's try the neural networks. Again, we're going to use the neural net package. And I'm going to define now a prediction function. And this is very useful because most of the time that's what you got to do. You define a prediction function that takes in the data set, computes the predictions, and applies these on the rows. Oh yeah, so it dichotomizes. This simply dichotomizes dichotomizes the outcome and then returns the dichotomized outcome. And here is the function, takes in the training predictors and the response, as well as the testing predictors and the response, specifies how many layers are we going to use in this neural net, and then calls the neural net with the training data, provides the corresponding layers information. Once it's done, calls the prediction with the test in, and then it simply reports the confusion matrix. And in this case, we use k equals to 5 folds, and I used only one iteration, which is kind of silly, but it did take a while because this is a real data set. I forget exactly how long it took, but it took a while. If you double B, it's going to take twice as long unless you use multiple cores or something. So here are the results. Accuracy 94%, sensitivity a little bit lower, but the specificity is higher. And overall 5.5 is not too bad for the log odds ratio. The next one is support vector machines. Earlier we used actually a different package for KSVM. Now here we're using the package E1071. Again, we're going to define an SVM prediction function that fits in the model, generates the predictions, and reports the results out. And we do this for linear kernel, 95% accuracy. The log odds ratio increased a little bit, so this yields a little bit better model. For the Gaussian alternative kernel, you have a slightly lower log odds ratio. Next one comes k nearest neighbors algorithm for classification. Again, we define yet another function, KNN predict. Here is how the model gets trained. KNN provide the training and the testing data, and only provide the classes for the training, not the testing. And then you specify that you want the probabilities to be reported in the model at the end. Confusion matrix again, cross-validate, and the results, they're actually, I think they might be printed at the end. Yeah, the results, these results I print actually at the end. K-means clustering is another method for clustering.
Question.
Yeah.
What is the value of K this segment?
The K?
Previous.
Oh, on the K nearest neighbors.
Yeah.
So in the K nearest neighbors, so this classification proceeds by randomly walking through and defining distances between subjects, okay? Using their features, define distances between subjects. And it seeds the algorithm by, suppose we're trying to classify the race that we all come from, or the country we come from. So we kind of, and if I want to use K is equal to 3, I say, I randomly select 3 people, okay? And then I measure our distances according to the features between all of us and every one of the 3 people that we chose as current centers. And then I assign to myself a racial or country label based upon which one is the closest one of these 3 people that I seeded. You know, I assign myself to this label, and then this proceeds iteratively by resampling the 3 kernels and walking around, and eventually these algorithms do converge, and it kind of tries to measure people that have common characteristics. K is a parameter that you can either computationally compute, or you can, most of the time you specify it right up here.
3.
Oh, I chose 3 because in this case, actually, let me see what did I choose here. Well, I see the K here is inferred from the number of levels that it finds in the training Y. It looks at how many labels are there, and that's the K that it's going to work with. But there is, you can use K nearest neighbors I would like to say unsupervisedly, but let me just think here for a second. Maybe not, I need to think about it a little bit. But in this case, because we didn't specify, I think it just accepts how many levels are there in the training set as the number of classes that it wants to beam people into. Okay, K-means is another method. Here is an example. I think we did that right. So here is the corresponding results for our PD data. All right, computing some of the okay, so this is the K++ is an algorithm that allows you to determine what the right K is automatically. And okay, so this is important here. Another way of classifying how good a classifier is by looking at the silhouette plot of the features. So right up here, it kind of shows you that it determined that there are two clusters, cluster 1 and cluster 2. The number of subjects that are binned into each cluster are reported, and then the average silhouette value is reported within each of these classes. Now the silhouette value is a reflection of how well the classification is, and there is 1, 2, 3, 4. 4 of the cases in the second class appear to be misclassified, and 1 of the cases in the first is misclassified. The other ones are pretty okay. The average silhouette plot for both of the clusters, however, is not too good. Typically, an average silhouette of less than 0.2 is considered to be marginal, not too good.
Question.
Yeah.
I need just a small confirmation. So KNN is a supervised method where we can manually specify, or we can specify like
right.
K. It's a supervised method. While K means clustering is an unsupervised cluster based on constituent values, it is forming clusters.
Right. Right. And right at the end here is where I show you guys how to compare. Okay, spectral clustering is the last one. You can look at some of the math. This is the spirals is an interesting thing. We do the income data as well. And now we want to do the comparison of the results. So here, I'm adding adaptive boosting to the Parkinson's disease as well. And okay, so here is where we're gonna bind together by rows all the diagnostic plots for adaptive boosting, linear discriminant analysis, quadratic, K nearest neighbors, legit, etc. Give them the appropriate names, and then this is a table that gets generated. So that's the typical table from which I tend to extract, obviously, the best approach for papers. Now, you typically don't report only one. You report a few just to show the differences or the amount of variability that you may see between different techniques. But certainly not all of them. I report them here just as a comparison purpose. Now, it's difficult. Okay, so I can't. Okay, the log odds ratio. When you have one of these things, you know, there is quite a bit of variation, but look at these log odds ratio for adaptive boosting. 97% accuracy. Sensitivity and specificity exceeding 93%. Log odds ratio 7.5, huge. Yeah.
Can you please briefly explain adaptive boosting?
So in adaptive boosting, what's happening is it randomly, so it fits in models multiple times by randomly seeding them, and then tries to pick the model that generates the best classifier at the end. Remember, stochasticity is very important, how you initialize an algorithm. And I showed you an example yesterday with a visual when I fit in the mixture model for the Gaussians, when I mix the three things together and then I try to untangle them by fitting a three Gaussian mixture model. Remember how unstable it was when I reinitialized it? It gave me always a different model. That same thing is happening exactly in all the machine learning methods. They're susceptible to the split between testing and training. They're susceptible to the seeds. There's a lot of stochasticity. So in adaptive boosting, these are expensive algorithms. You do this multiple times with multiple seeds and essentially aggregate at the end the best performer, and that's what you get to report at the end for your statistics. So most of these, with the exception of, look, K-means performed really poorly here, you know.
Excuse me, sir.
Yeah.
Is there any process in which we can optimize or decide on the bad algorithm? Like if I want to use other boost and different algorithms along with the problem, how can I do it?
You can boost pretty much any algorithm. I believe in the Adam method, we may have to look at this, but I believe in the Adam method that we had up here, right in my definition, let me just see real quick. Oh, it's all the way up there somewhere. You may have to specify exactly which method you want to boost. And I believe I had some description of this. It was in a different chapter. We can look this offline if you want at the end to show you some more examples of boosting. Boosting and bagging, right? These are two strategies that allow you to enhance the performance of machine learning methods. Yeah, I think it's in chapter 14 is where we talked about it. So, all right, so you end up with something like this at the end, and you know, you essentially choose one method that may be working.